the date does sound, the earth is round. Like an apple or a melon, being sailed by brave Magellan. Yet you ask, is this all true? What the hell, what's wrong with you? Like a snowball or a beat, it spins through space, it's really sweet. Your lack of science is quite rife. Goodness gracious, get alive. Round, 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 the earth is round. Smart people found that the earth is round. There's proof abound, don't fool around. The date does sound, the earth is round. Like an apple or a melon, being sailed by brave Magellan. Yet you ask, is this all true? What the hell, what's wrong with you? Like a snowball or a beat, it spins through space, it's really sweet. Your lack of science is quite rife. Goodness gracious, get alive. Round, 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 the earth is round. Smart people found that the earth is round. There's proof abound, don't fool around. The date does sound, the earth is round. Like an apple or a melon, being sailed by brave Magellan. Yet you ask, is this all true? What the hell, what's wrong with you? Like a snowball or a beat, it spins through space, it's really sweet. Your lack of science is quite rife. Goodness gracious, get alive. Round, 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 the earth is round. Smart people found that the earth is round. There's proof abound, don't fool around. The date does sound, the earth is round. Like an apple or a melon, being sailed by brave Magellan. Yet you ask, is this all true? What the hell, what's wrong with you? Like a snowball or a beat, it spins through space, it's really sweet. Your lack of science is quite rife. Goodness gracious, get alive. Round, 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 the earth is round. Smart people found that the earth is round. There's proof abound, don't fool around. The date does sound, the earth is round. Like an apple or a melon, being sailed by brave Magellan. Yet you ask, is this all true? What the hell, what's wrong with you? Like a snowball or a beat, it spins through space, it's really sweet. Your lack of science is quite rife. Goodness gracious, get alive. Round, 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 the earth is round. Smart people found that the earth is round. There's proof abound, don't fool around. The date does sound, the earth is round. Like an apple or a melon, being sailed by brave Magellan. Yet you ask, is this all true? What the hell, what's wrong with you? Like a snowball or a beat, it spins through space, it's really sweet. Your lack of science is quite rife. Goodness gracious, get alive. Round, 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 the earth is round. Smart people found that the earth is round. There's proof abound, don't fool around. The date does sound, the earth is round. Like an apple or a melon, being sailed by brave Magellan. Yet you ask, is this all true? What the hell, what's wrong with you? Like a snowball or a beat, it spins through space, it's really sweet. Your lack of science is quite rife. Goodness gracious, get alive. Round, 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 the earth is round. Smart people found that the earth is round. There's proof abound, don't fool around. The date does sound, the earth is round. Like an apple or a melon, being sailed by brave Magellan. Yet you ask, is this all true? What the hell, what's wrong with you? Like a snowball or a beat,
Hello everyone, how are you all doing? Thank you all very much for joining me for the second month for Backyard Astronomy lecture. Apologies, I'm going to start off by saying apologies now for my voice. It's a little bit hoarse. I've had a bit of a cold over the last few days. And I've done I did 12 miles this morning as well, so cold got the better of me, I think. So if for whatever reason I run off to get a drink, I've got a bit of a cup of tea, but I might have to top it up in a bit. So apologies on that one. Also apologies, I've dropped off comments on social media a bit recently. I did write a post about it, but the marathon training is quite tough. It's taken a lot out of me, and when I finish a long one, I just want to go in and do nothing basically. So so for the time that I'm doing the training, I won't be as active online, but the videos will still keep coming. Okay, so second lecture. Before I start, someone pointed out last month, really good point, I didn't mention any source material for the information I got for the first lecture. Majority of that I got from this book here, which is The Universe, or A Brief History of the Universe by J.P. McAvoy. Really, really good read. Goes into a lot more depth in terms of the movers and players in the history of astronomy. I picked out obviously the most commonly known ones and the kind of the most important parts of it, but if you want to have a look at the complete history of it, then that book is a definite recommendation. Okay, so how many got? 588 watching. Brilliant. Right. I'll do a slightly different format this time. I'm not going to, any super chats that come through, I'm not going to shout them out straight away. Christian Bourne, thank you very much. I'm going to go for as many as I can when I come to a natural break in the lecture. Shouldn't be as long as the first one. The first one's normally quite long because it's quite a long story, but that doesn't mean there's going to be less content. As I said before, if you're already into astronomy, you'll probably find a lot of this quite boring and stuff that you already know. This purely is for anyone who wants to get into it and wants to start. It's all the information, kind of key bits and bits and pieces you need to know. So, let's go. Okay, lecture 2. So the majority of this is focusing on what we can see with just our eyes alone. No instrumentation, no binoculars, no telescopes, nothing like that. How we can use our eyes to view the night sky, because that's where everyone starts. Excuse me. Okay, so if I said to any of you guys, could you point out the North Star in this image? I expect a lot of you who are all into astronomy could quite quickly. But anyone who doesn't really know much about the night sky, I feel couldn't. I was out with a group of friends a couple of weeks ago. There was 7 of us in total, and it was clear night, and I said to anyone, can you point out the North Star? And all 6 of them failed. 2 people even believing it was the brightest star in the sky, which is quite a bit of a myth. So I'm sure a lot of you can see it, but this is taken from a piece of software called Stellarium, and it doesn't always give the best representation of how the stars look, but it has a good kind of accurate representation of the constellations and where the stars are. And the North Star is this one here. I hope you can see the little red pointer. I'll show you a little bit later how you can find it, but from this picture and this software, it looks a lot brighter than it does in reality. It's actually not really that bright at all, the North Star. Okay, so before we start looking at things like that, we need to look at something called the celestial sphere. Now, the celestial sphere is something that astronomers use to kind of pinpoint all the stars in the sky. It's like a little map for us to tell us exactly where the stars are. So obviously to us, the stars appear to occupy fixed positions relative to each other. And obviously distance is a huge factor in that. There are stars that do move, have proper motion. That's a little bit more complex, but for all intents and purposes, the stars look like they occupy fixed positions relative to each other. So if we imagine that the Earth is rotating inside a much larger sphere, then we've got a good model for how the night sky appears to us. So we've got the Earth here, and if we imagine that it's rotating inside a much larger sphere, and all those stars are projected onto that sphere. So the stars occupy the fixed positions on the surface of this celestial sphere, and almost like it's transparent and we can see through it. If we extend the North Pole outwards, then that point that meets the celestial sphere is the North Celestial Pole. And by the same extension, if we extend the South Pole, then that point is the South Celestial Pole. And if we extend the equator, then we have the Celestial Equator. If we extend it out and it reaches the celestial sphere, we've got the Celestial Equator. Okay. Next thing we've got is the zenith. Now the zenith is the point on the celestial sphere that is directly above the observer, and it's exactly 90 degrees from any point on the horizon. So if you're stood in a field here, and we've got the celestial sphere surrounding the Earth, the zenith is the point on the celestial sphere that is directly above you. We're concentrating purely on the observer here. That's what we call the zenith. Okay, next thing is the meridian. Now the meridian is a giant circle which passes through both the celestial poles and the zenith. It's perpendicular to the celestial equator, and it looks like that. So here you are in the field again. So the zenith is the point directly above you, and the meridian is an imaginary line that passes through the zenith and both celestial poles. So like that. Excuse me. Hope everyone's with me so far. Okay, next thing is the ecliptic. So the ecliptic is the apparent path of the sun's motion on the celestial sphere. I say apparent path because obviously it's not moving. The projection of Earth's orbit onto the celestial sphere is kind of also how we would perceive the ecliptic. And it also marks the line along which the planets, the moon and the asteroids wander, more or less. It's essentially the plane of the entire solar system. So here is, go back, here is a little image of the Earth, and it's not in its normal tilt, it's upright. So the celestial equator is kind of level, and the ecliptic would look like this. So essentially, like I said, the ecliptic is the plane of the solar system. So it's how we can perceive the solar system in terms of where it is compared to us. Okay, so here we have from that piece of software, Stellarium, a picture of the ecliptic, so it's marked on there, and the planets and the moon, and the planets and the moon in tow. And I was going to say the sun, but it's down there. So the planets and the moon are in tow. You can see them all roughly along that line. Obviously, the solar system isn't completely, I don't want to say the word flat. Obviously, it's not completely a level plane, but there is a slight variation in terms of the angle of how we perceive the planets, but essentially they all follow that ecliptic. Okay, declination. So on the celestial sphere there are lines of declination, and it's the angle of a star from the celestial equator, and obviously that's based on the celestial sphere. It's very similar to what we would perceive to be latitude here on Earth, which denotes the angle of a place on Earth's surface in relation to the equator. So the celestial equator is said to have a declination of 0, and Polaris, the North Star, has a declination of 90 degrees. So if you have a look at this little image here, if we're on the Earth here, then we're viewing stars on the celestial sphere, and wherever that star is in relation to the celestial equator, the angle from the celestial equator to that star is its declination. As you can see, there's the 0 degrees, here's 90 degrees, and anywhere from here to here could be between 0 and 90. If we're going from the celestial equator to the south celestial pole, then it's in the negative numbers. It's 0 to minus 90. Don't want to be a northern hemisphere chauvinist. We've got to think about the southern hemisphere people too. So how do we measure that? So the declination coordinate is often written like this. So the first number there is a value of degrees. So like I said, it's the degrees from 0 to 90 in the positive or negative, however far it is from the celestial equator. The second number there is what we call arc minutes. And there's 60 of those per degree. So it's a way of breaking that degree down so we can be more accurate when we're looking for celestial objects. So there are 60 arc minutes in 1 degree. And you might have already guessed, but this number here is arc seconds. And there are 60 of those per arc minute. So just so you've got that, degrees, arc minutes, arc seconds. That's a coordinate of declination. Okay, so the second coordinate we would look at is what we call right ascension. So there we can see the lines of right ascension. And right ascension is very similar to longitude here on Earth. It's the 0 point here is obviously here in the UK at the Greenwich Observatory. And the 0 point for right ascension on the celestial sphere is the spring equinox. So here we have the declination part here. So this is the angle here from declination, and from the equinox, wherever the star is in relation on the celestial equator, or from the vernal equinox, that will be its right ascension value. So we get two coordinates, essentially, a declination and a right ascension, whenever we are looking at celestial objects. So how do we write those down? That one's written like this, and this looks obviously really familiar. Looks like time. So obviously the 5 is in hours, the 41's in minutes, which we know there are 60 of them in an hour, and the 28 is in seconds, which we know there's 60 in a minute. The Earth rotates once in 24 hours, so it's fair to say that the Earth is split into 24 segments, or the celestial sphere is split into 24 segments. And if we want to narrow down on that, we can turn those segments into minutes and seconds. Okay, so I'm actually going to test you guys now. So as long as you can see that all right, if you're on a screen that's big enough. So on the left here we have 4 celestial coordinates, the declination and the right ascension, or the right ascension and declination. And on the right here we have a picture taken from Stellarium of Orion, the constellation of Orion. So we have our right ascension grid lines here. So here we've got 7 hours, 6 hours, 5 hours. And we have our declination lines here. So there's 0 degrees, 5, 10, 15 degrees, minus 5, minus 10 degrees. So what I want you guys to do, I'll give you a few minutes if you want to have a look. Look at these 4 coordinates, and I want you to try and tell me which star is which coordinate. So I'll give you a few minutes. So if you want to write down in the chat, 1 equals whatever, 2 equals whatever, and we see how you go. I did see a super chat. Call of the Void, thank you very much. Have a quick look at the chat. So I'll give you a couple of minutes. George Hartman says 1 is Betelgeuse. No, that's not correct. Lucas, Thank you very much. Keep up the good work. I really enjoy your content and always look forward to watching your videos Tuesday and Friday, usually whilst driving. Thank you, Lucas. I have a typo in line 2. Ventus Pains, well done. Number 1 is safe. Vampire Darkness, number 2 is Bellatrix. Good. Alex, don't worry about it, buddy. Rewatch the video. Riders of the Lost Park. Spot on, well done. So 1 is safe, 2 is Bellatrix. Anyone want to have a go at 3? Mr. TW88, well done. That's what they're all correct. So yes, 3 is Cursor. And number 4, Alex K, well done. 4, Mintaka. 4 is the most difficult because it's so close to the other 2. That's Orion's belt, obviously, but well done. So I hope you get the gist of that. The Phantom Stag, thank you very much. So this is just obviously a fairly small portion of sky, and it's a good way of kind of getting used to how these coordinates work. So declination, right ascension. Hope you all got that. If you didn't, then please do check the video back again, see how we do it, and have another go. Okay, moving on. Now we should really talk about the constellations of the Zodiac. They are the 12 constellations which the sun passes throughout the year. And if you're into star signs and all that, then you would be of the nature to go and look in a magazine and have a look at your star sign, which obviously is the constellation that the sun was in on the day you were born. Now my birthday is November the 19th, which means that according to this, that the sun was in the constellation of Scorpio on the day you were born. However, anyone who does read their star signs or horoscopes, or if you know anyone, you can gladly tell them that they've been reading the wrong one their whole lives. So these constellations they're thousands of years old, 2,000 to 3,000 years old, and in that time the Earth has done something which we call precession. So basically it wobbles on its axis as it spins. When it does that, it kind of obviously the constellations shift a little bit to our point of view. So on the day I was born, the sun was not actually in Scorpio, it was in Libra, which is the constellation next door. Because in those last 2,000 years it shifted enough that it's changed. So if you all think about your star sign, so I'm Scorpio, you need to move one place clockwise to know your actual star sign. So as I said, I'm supposed to be a Scorpio, but the day I was born, the sun was in Libra. If you don't believe me, get Stellarium, it's free software. Go back to the day you were born and have a look where the sun was, what constellation it was in, and I think you will find it's in the wrong one. So anyone who believes heavily in that, you can ruin their world with that one. But it is important to talk about them because they are 12 of the most well-known constellations. Okay. If we're going to talk about viewing stars, it's quite important that we talk about magnitude. And magnitude is the relative brightness of a star as seen from Earth. Now there's two different types, apparent and absolute. Now apparent magnitude is how luminous a star or bright a star will look to us here on Earth. Absolute magnitude is how luminous a star is from a standard distance in astronomy, that we kind of figure that out with a very complex set of calculations. But all we need to know really is the absolute magnitude is its intrinsic brightness, and the apparent magnitude is how we perceive it based on distance and size of that star. The lower the number on the scale, the brighter the star is. And the magnitude depends on a lot of things, but primarily how big that star is and how hot that star is, and crucially how far away that star is. Now Sirius has a magnitude of minus 1.46, and Sirius is the brightest star in our sky, if it's visible at that time of year. Polaris, the North Star, only has a magnitude of 1.97, which is relatively dim. And Jupiter, when it's at its brightest, will have a magnitude of minus 2.7, so it's far brighter than any star in the sky. And most planets are, not most, Venus and Jupiter, sometimes Saturn, are brighter than most stars. Quick question in the chat. If you're in a dark sky space, how many stars do you think you can see on a clear night? So no light pollution involved. How many stars do you think you can see just with the naked eye? Stephen Latman, feel better Dan, love the lectures, thank you very much. So I know we're a bit behind, but we'll see what sort of guesses we'll get from that. Gary Isla White says 2,000. Tommy says 150 million. Where's Wally says 12. Trillions, billions, billions. Too many to count. Dan 74, nice. Over 9,000, 10,000. Young Blue Skeptic, 10,000. Whoa, loads of numbers coming in. Okay. I would say no more than 6,000 you could see with the naked eye on a clear night. Dark sky space. No more than 6,000. So, depending on where you live and the kind of light pollution you have, depends on what sort of magnitude stars you can see. If you live in what we would call an inner city sky, the highest magnitude visible is a 0. The highest magnitude. Now remembering that the scale is backwards, so the lower the number the brighter it is. That pretty much means the North Star is not visible in an inner city sky. Light pollution is too much. If you're in a suburban urban transition, so if you're somewhere between the city and a nearby town, the highest magnitude you could see is +2. So at this point, North Star probably will be just about visible. In a suburban sky, the highest magnitude you'll be able to see is a +3. A rural sky +4. And if you're in what we would call an excellent dark sky site, we're talking a +5, +6. So obviously, the less light pollution there is, the more stars you can see and the more dimmer stars you can see. But it's important we know about magnitude, because when we look things up, different stars that we might want to look at, we can look at its magnitude, and we'd know if it's visible at any point where we are because of its magnitude. If you see a star that's got a magnitude 8, you know you're not seeing that without a telescope, possibly a good pair of binoculars. If it's got magnitude -1, it's going to be easily visible. Okay, so excellent point to just take a break. I'll have a quick look to make sure there's any super chats. The Snark, thank you very much. I think that's it. And we did Stephen Latman, yep. Okay, great. Cool. We will move on then to constellations and stars. So, the Snark, buy a good whiskey to chase the bacteria. I will. Thank you. So it's quite important that we know a little bit about some of the constellations and some of the more brighter stars in the sky, because we can use them as like reference points when we're out viewing. And we'll start with Ursa Major, which is kind of a biggie if you're in the Northern Hemisphere. So Ursa Major, so most of you will know the Plough or Big Dipper or whatever you want to call it, which is actually the back end of Ursa Major. It's supposed to be a big bear, so it's Great Bear. And these 7 stars here, the Plough, are the 7 brightest stars. Ursa Minor, on the other hand, is nowhere near as big. So this is kind of, so Ursa Major, Great Bear, Ursa Minor, Little Bear. And the North Star Polaris is part of Ursa Minor. So it's kind of, some people call it the Little Dipper. So you can see the Big Dipper here. And if you trace out a line from these 2 stars here, Merrick and Doob, then you can kind of draw a line and get to Polaris. Now, when you get to Polaris, unless you're in a pretty dark sky spot, you're not really going to see many of the other stars in the constellation. Polaris is the brightest one. If you do, you'll see a small little dipper, and that is Ursa Minor. So I always think it's fun to look at the myth of these constellations. And this one's a good one. So Callisto. Callisto was a nymph of great beauty that was walking in the forest one day when she grew tired and laid for a rest. Zeus saw her and immediately fell in love with Callisto, obviously, and they bore a child called Arcus. Now, Hera wasn't too happy about this, which I'm not surprised about. So she turned Callisto, this nymph, into a bear. Now, Arcus grew up and he became a hunter. And one day he was out in the woods walking and he saw his mother in bear form, but obviously he didn't know it was his mum. She, forgetting for a bit that she was a bear, rushed towards him. Arcus thought she was attacking him and he drew his bow to kill her. He was a hunter after all. But Zeus saw what was going on. He intervened. He thought, I can't be having any of this. So he turned Arcus into a little bear, grabbed them both by their tails, and swung them up into the heavens. And that's the myth on how those 2 constellations came to be. And here they are. Now, Hera, though, that wasn't good enough for her. So she had a quick word with Poseidon, who was obviously the god of the sea. And she made sure that the 2 of them would never bathe in the sea. They would be destined for a eternity of dirtiness. So that's why they circumnavigate Polaris, never dipping below the horizon, never bathing in the sea. The ultimate punishment from Hera. Eternal dirtiness. Okay, so we talked about Polaris in Ursa Minor, but it'd be quite nice to know a little bit more about it as a star. So Polaris is pretty unimpressive, actually. To the naked eye, it ranks about 50th in terms of the brightest star. As I mentioned before, it's not all too magnificent, but it is actually 7 times bigger than our sun. Now, if we took a 10p piece and we held it at arm's length, that would just about cover up the sun. I don't advise doing it for obvious reasons, but the moon looks pretty much the same size as the sun in the sky, so try it with the moon, 10p piece at arm's length. Now, if Polaris was at the centre of our solar system, you would need a dinner plate at arm's length to cover it up. It is much bigger than the sun. And it's also 2,000 times more luminous, but it's 432 light years away, so Polaris doesn't appear that bright, which we've seen. And if you've seen it for yourself, you'll know it's not at all that bright. Okay, Cassiopeia. So Cassiopeia Looks like, depending on which way around it is at the time you look at it, looks like a W or an M or a 3 or however you want to look. They're fairly bright stars compared to the stars around them. Best way to find it is, so the 2 pointer stars from the Big Dipper, like I said before, draw a line, you get to Polaris, the North Star. If you carry on going about the same distance, you'll see a W-shaped constellation or an M-shaped constellation, and that is Cassiopeia. Pretty hard to miss. There's some of the constellations that are directly surrounding it. So like the myth of this one. Now Cassiopeia was the queen of Ethiopia. She was beautiful, arrogant and vain. She would spend her days boasting that her daughter Andromeda was the most beautiful woman on earth, even more beautiful than the sea nymphs themselves. Poseidon wasn't happy about this, so he sent a sea monster to destroy Cassiopeia's kingdom. And the only way to get out of it would be to place Andromeda at the sea's edge as a sacrifice. Only way they can get out of the complete destruction of their kingdom. So what did they do? They obviously put Andromeda to be sacrificed. Why wouldn't you? You don't want your kingdom being destroyed, would you? So they accepted it and they hung her out to dry. Fortunately though for Andromeda, Perseus was flying by on Pegasus and he said, yep, I'll save her, picked her up, flew her off, and she was okay. However, Poseidon decided as punishment for her ways, Cassiopeia would spend an eternity in the stars, with her head pointing at Polaris, so she spent half the night upside down. Also, Cassiopeia is a circumpolar constellation, so also dirty. Right, Orion. Now this is a beautiful constellation, one that is visible both in the northern and southern hemisphere, depending on the time of year. And it's a treasure trove of stars, deep sky objects. It's brilliant if you want to get out and view some stars and bits and pieces like that. So it's only visible in the northern hemisphere from late autumn to early spring, but it is one of the most recognisable constellations. As I said, it's a treasure trove of deep sky objects as well as stars. And the first one we're going to look at is Betelgeuse. So you might recognise the Betelgeuse from the coordinate quiz that we did earlier. And it's much cooler than the Sun. The Sun is a very, very ordinary star, but it is hotter than Betelgeuse. And that kind of means, because it's cooler, that it's 100,000 times more luminous than the Sun. 100,000 times more luminous. It's what we call a red supergiant, and it's 450 light years away. It is very, very late in its stellar evolution, and it's likely to go supernova very soon. Now, very soon, astronomically speaking, is any time between now and the next million years. If it does go, and we are able to see it, of course, being 450 light years away, it could have already gone, but it's just taking time to get the light. It takes time to get here. If it does go, it'll be the brightest star in the sky, as bright as the moon and visible during the day for about 2 weeks. And it's massive, and I cannot stress enough how big it is. If you take a look at this little image here, this is an image taken of Betelgeuse. It's so big that we can actually get images of it. And here's a key underneath. So this is the size of the star compared to the size of Earth's orbit, not Earth, Earth's orbit. And this is the size of Jupiter's orbit. So we're talking about a star that if we put it at the centre of the solar system, everything up to Jupiter engulfed. It is huge. Rigel up next. Now Rigel is, so Betelgeuse is the top left, the orangey, cool orange star. Rigel is the exact opposite in the bottom right, and it is very, very young, extremely hot, only 10 million years old, which is a baby for a star, but it's so massive it's already exhausted its hydrogen fuel. It sits approximately 850 light years away. It's twice as far away as Betelgeuse, but it's also twice as luminous. So that's why they appear similar brightnesses in the sky, 7th and 9th respectively. So 200,000 times more luminous than the Sun. The surface temperature of Rigel is so blisteringly hot that if it was at the centre of our solar system, Earth would need an orbit 5 times further away in order for liquid water to exist and by extension life to exist. It is a surface temperature in excess of 40,000 degrees. The Sun's is 6,000 degrees. So we're talking an extremely hot star. Sirius. Now, here we go. Here's Betelgeuse, top left, Rigel, bottom right. Now, if you can find Orion, which is pretty easy to find, if you look to the left of Orion, kind of the lower left, you'll see a very bright star, often kind of shimmering with lots of different colours, called Sirius. Now, Sirius is the brightest star in the sky, as I mentioned earlier. Now, Sirius isn't actually one star, it's a double star system. Sirius B is a white dwarf. So we'll talk a little bit more about different stages of stellar evolution on a later lecture. But a white dwarf is essentially a star that's come to the very end of its life. It's kind of like in the stellar old people's home. And this is a double star, so they orbit each other. Sirius A is a hot white star, Sirius B is a white dwarf. It's so bright, or it appears so bright to us, because it's only 8.6 light years away. I say only, that's still a massive distance if we're talking about humans, but astronomically speaking, 8.6 light years is pretty close. It's a white main sequence star, about twice as massive as the Sun. It's known as the dog star because of its prominence in the constellation Canis Major, Great Dog. Okay, Summer Triangle. Now, the Summer Triangle is called so because it is viewed best in the summer in the Northern Hemisphere. Excuse me. And it's made up of 3 stars: Deneb, Vega and Altair. So Deneb is in the constellation of Cygnus, Cygnus the Swan. We also call this one the Southern Cross, these stars here. Vega is in the constellation of Lyra. Vega is due to be our North Star in about 10 to 15,000 years. And Altair is in the constellation of Aquila. And these 3 stars make up the Summer Triangle. They're very bright compared to the stars around them. And the Summer Triangle can easily be seen. It's very large in the sky. And it's a good one to try and spot if you're out and about in your back garden. Okay, right, so that just about wraps up the second lecture. I do have some homework for you if you want to do it, and that is this: go outside if the weather allows you. Take a look in the sky. If there's no cloud cover or anything like that, try and find Orion and try to identify Betelgeuse, the orangey star, Rigel, the blue one on the bottom right, and Sirius, which is the one to the lower left of Orion. Try and identify those. If you do, brilliant. You're already halfway because you're identifying stars. The colour situation, so colour is denoted by temperature. So if you ever have a look up at the night sky and it is dark enough and you look for long enough, you'll notice that they are different colours. They range from blues to oranges to reds to whites to yellows. Basically, red, orangey red is a cool star, all the way through to orangey yellow, yellowy white, white blue, and blue are the hottest stars. So have a look at those. Thank you all very much for joining me. Did we get any more? Call of the Void again. Thank you very much. Really feel bad for you. Get well soon. Thank you. hopefully I'm coming to the end of it now. It's just my voice now. I have to record tomorrow as well, so that'll be interesting. Thank you very much for joining me. Next month will be lecture 3. It'll be the first Sunday of March. It'll be all about the solar system, not just about the planets, all about the cool little moons as well, a bit on the formation of the solar system, and when we can view the planets and stuff like that, the best time to view them. Should be an interesting one. It's one of my more favourite ones, that lecture. Thanks for joining me. I'll see you all. Michael Van Reenen, thank you very much. I'll see you all on Tuesday, where, believe it or not, I'll be looking at a video from a guy that doubts that England, my home country, is a real place. I know. Look forward to that one. And that's about it. So I'll see you all Tuesday. Have a great week. Good night.